Again, welcome to Operating System CS332 class. This is the final session of Chapter 6 of the course textbook, which is Concurrency, Deadlock, and Starvation. So in our previous section 6-1 and section 6-2, we discussed about the concept of deadlock, how to prevent it, and also how to avoid it. Also, we discussed about starvation. So in these lectures, we're going to discuss about different operating system mechanisms for solving those problems also. That's the deadlock and starvation. So we start with the units. Normally, units provide different mechanisms for interprocess communication and synchronization. So in this section, we are going to look at pipes, messages, shared memory, semaphores, and signals. Again, chapter 5, we talk about the concept of semaphores, also signals. So here we say pipes, messages, and shared memory can be used to communicate data between processes. So again, with pipes, messages, and shared memory, we can use them to again communicate data between processes, whereas the semaphores and signals can be used to trigger actions by other processes. So again, we use the pipes, messages, also share memory to communicate data between processes. Then semaphore and signals, we normally use it to trigger actions by other processes. So again, one of the most significant contributions of UNIX is the development of operating system and pipe. So we start with the pipe. It's very, very important. One of the most significant contributions of UNIX is the development again of the operating systems pipe. And this is inspired by the concept of co-routings. So a pipe is a circular buffer. Actually, that's why it's called pipe. The concept of a circular buffer is the same as a circular queue. So we have a buffer is a memory space. So when we reach at the end of the memory space, we join the end to the beginning. So the buffer becomes a circle, so a circular buffer. So a pipe is again a circular buffer that allows two processes to communicate on the producer-consumer model. So circular buffers that allow two processes to communicate on the producer-consumer model. And the concept here also is using the queue implementation, which is again first in, first out queue. Written by, again, one process, then read by another process. Now, when a pipe is created, it is given a phase size in bytes. So when a process attempts to write into the pipe, the write request is immediately executed if there's enough room or sufficient room. Otherwise, the process is blocked. So again, anytime a pipe is created, is given a phase size. So when a process is attempting to write into the pipe, which is a memory location, the buffer, a circular buffer, the request is immediately executed if there's enough space in the circular buffer or in the pipe. Otherwise, the process again is blocked, which means again, there's no space. Similarly also, when we are reading process, a reading process will be blocked if it attempts to read more bytes than are currently in the pipe. It will be blocked because no space. Otherwise, the read request is immediately executed if there's enough space in the pipe. So the OS again enforce mutual exclusion. That is, only one process can access a pipe at a time. So this is the same idea as we were talking about deadlock in our previous chapter, mutual exclusion. So there are two types of pipes. Again, we have the name and also unnamed pipes. Only the related process can share unnamed pipes, while other related or unrelated process can share named pipes. So a message also is a block of bytes with an accompanying type. And normally UNIX provide message send and message receive. Again, that's message send is MSG SND, MSG RCV is message receive system calls. So normally UNIX provide those two system calls, message send, message receive, for process to engage in message passing. Associated with each process, again, will be the message queue, which also function like a mailbox. So a message sender normally will specify the type of message which each message sends, and this can be used as a selection criteria by the receiver. So in this case, the receiver can either retrieve messages in first in, first out order or by type. So a process will block when trying to send a message to a queue that has no space. So a process also will block when trying to read from an empty queue. So if a process attempts to read an empty message of a certain type and fails because no message of that type present, in this case, the process is not blocked. So the whole concept here again is the shared memory concept. Also, the fastest form of interprocess communication provided in UNIX is the shared memory. So fastest form of interprocess communication. And this is a common block of virtual memory shared by multiple processors. It's a virtual memory. So here the process either read and write a shared memory using the same machine instruction they use to read and write other portion of their virtual memory space. Permission is read-only or read-write for a process. This can be determined on a per process basis. Also, the mutual exclusion constraints are not part of the shared memory facility, but must be provided by the process using the shared memory. So again, permission is read-only or read-write for a process. The next section will be the semaphores. Again, chapter 5, we talk about what is a semaphore. So UNIX again uses a semaphore. So semaphore system calls in UNIX system are generalization of semblait and also semsignal. So generalization of semblait and also semsignal primitives. Again, this is defined in chapter 5 of the course textbook. Covered this in previous. So several operations can be performed simultaneously, and the increment and decrement of operations can be values greater than 1. Also, the kernel does all of the requested operation atomically. No other process may access the semaphore until all operations have completed. So here we see a semaphore normally consists of the following element. First, the current value of semaphore, and also the process ID of the last process to operate on the semaphore. And now the number of process waiting for the semaphore value to be greater than its current value. And the number of process waiting for the semaphore value to be 0. Now, associated with the semaphore are queues of process block on that semaphore. So semaphores are actually created in sets, with a semaphore set consists of one or more semaphores. Also, there's a SEM control system call. So the SEM control system call that allows all of the semaphore values in the set to be set at the same time. Also, we have the SEM op system call, SEM operation system call that makes an argument a list of semaphore operations. So each will define on one of the semaphores in the set. So next we talk about the signals, which is also provided by the UNIX. So here we see a signal is a software mechanism that informs a process of the occurrence of asynchronous events. So a signal is similar to a hardware interrupt, but does not employ polarities. There's no polarities. That is, again, all signals are treated equally. So signals that occur at the same time are presented to a process one at a time with no particular ordering. So again, process may send each other signal, or the kernel may send signals internally. A signal is delivered by updating a field in the process table for the process to which the signal is being sent. So again, a process may respond to a signal by performing some default actions, or executing a signal handler function, or by ignoring the signal. So the next will be the real-time signals. So learners also include all the concurrency mechanisms found in other UNIX systems, including the pipes, messages, shared memory signals. But also learners support the special type of signaling known as, again, the real-time signals. So the real-time signals are part of the POSIX-1B real-time extension feature. So RT normally signals differ from standard UNIX or POSIX-1 signals in 3 ways. So one, we said signal delivery in priority order is supported. Also, the multiple signals can be queued. And with standard signals, no value or message can be sent to the target process. So next we have the atomic operations. And here also the learners provide a set of operations that guarantee atomic operations on a variable. These operations, again, can be used to avoid simple race condition. Also, an atomic operation executes without interruption and also without interference. On a uniprocess system, a thread performing an atomic operation cannot be interrupted once the operation has started until the operation is finished. In addition, on a multiprocessor system, again, the variable being operated on is locked from access by other threads until this operation is again completed. So again, we have two types, the integer operations and also the bitmap operations. That's the simplest form of approaches to kernel synchronization. So with the integer operation, we say that it operates on integer variable and also typically used to implement counters. bit mount operations normally operate on a sequence of bits at an arbitrary memory location indicated by the pointer variable. So again, we have two types of atomic operation that are defined in LINUX. The first at the top, we have the integer operations. The second, we have the bitmap operations. Again, this table can be found on page 289 of our course textbook. The text here is very small that it's difficult for me to read it or explain. So we can see all the functions for atomic integer operations and also atomic bitmap operations, the functions we can do. For example, we can, the bitmap, we have set bit. So set bit function, we set the bit NR in the bitmap pointed to by address or ADDR. We also have the clear bit. This will clear bit NR in the bitmap pointed to by address. By default, we have the NR as our argument. So next we talk about the concept of Spinlocks. So this is the most common techniques for protecting the critical section in LINUX. The most common techniques used for protecting critical section in LINUX. It's called the Spinlocks. Now, only one thread at a time can acquire a spin lock. Any other thread attempting to acquire the same lock will keep trying, that's spinning, until it can acquire the lock. So that's why it's called a spin lock, spinning. In response, a spin lock is built on an integer location in memory that is normally checked by each thread before it enters its critical section. Now, if the value is 0, then the thread sets the value to 1 and enters the critical section. Now, if the value is non-zero, then the thread continually checks the value until it is 0. So these are some of the functions for LINUX Spinlocks. We have the Spinlock IRQ. So Spinlock IRQ normally is like a Spinlock, but also disable interrupts on the local processor. Then we have the spin unlock function. This will release a given lock. So here we discuss about the semaphores. We have the user level. So normally LINUX provide a semaphore interface correspond to that in UNIX SVR4. So again, we also have the internal. This normally again implemented as a function within the kernel and are more efficient than user visible semaphores. Now we have 3 types of kernel semaphores: the binary semaphores, counting semaphores, and also reader writer semaphores. So this is again the LINUX semaphores. So binary and counting semaphores defined in LINUX 2.6, which is our table 6.5, have the same functionality as described for search semaphores in chapter 5. So the function names down and up, and normally are used for function refer to. In example will be there's semaphore wait and semaphore signal respectively. Now a counting semaphore is initialized using the sema-init function, which gives the semaphore again a name and assign an initial value to the semaphore. Now binary semaphores called the mutexes or mutex in Linux are initialized by the initial mutex and initial mutex log functions. And this is our Linux memory barrier operations. Now to enforce the order in which instructions are executed, Linux also provide a memory barrier facility. And so it lists the most important functions. As we can see, most of the important functions are defined for its facility. We have the RMB function. This operation will ensure that no reads occur across the barrier defined by the place of the RMB. Also, we have the ready copy update, RCU. So ready copy update is a mechanism in an advanced lightweight synchronization mechanism, which was integrated into Linux kernel. So the RCU again is used widely in the Linux kernel. For example, in the networking subsystem, the memory subsystem, also the virtual file system, and more. So RCU is also used by other operating systems. Example, Dragonfly BSD uses mechanism that resembles Linux sleepable RCU. As opposed to common Linux synchronization mechanism, again, RCU normally readers or the readers are not locked. They don't get locked. So the shared resources that the RCU mechanism protects must be accessed through pointer. We also have the mutual exclusion. Again, we discussed about mutual exclusion Mutex in our chapter 5 of the course textbook when we are discussing about, again, the deadlocks and also critical section problems. So normally a mutex is used to ensure only one thread at a time can access the resource protected by the mutex, and this concept against the critical section problem. And here we see again the thread that locks the mutex must be the one that unlocks it also. So again, mutex is used to ensure that only one thread at a time can access the resource protected by the mutex. So the thread that locks the mutex must be the one that unlocks it. A thread's attempt to acquire mutex lock by executing mutex enter primitive. So always a thread that is attempt to acquire mutex lock by again executing the mutex enter primitive. Now, if the mutex enter cannot set the lock, because again, most likely it's already set by another thread, then the blocking action depends on the type specific information stored in the mutex object. So the default blocking value is a spin lock. and a block thread pulls the status of the loop lock while executing in a busy waiting loop. So the default blocking policy is again a spin lock, and an interrupt-based blocking mechanism is an optional. So next we talk about the semaphores. Here we say that Solaris provide the classic counting semaphores with the following primitives. So a writer lock allow multiple read to have simultaneous read-only access to an object. So again, Solaris again provide classic counting semaphores. So here we have the semaphore P. This will decrement the semaphores, potentially blocking the thread. Then we have a semaphore V. This will increment the semaphore, potentially unblocking it. Then sema-tribe, decrement the semaphore if blocking is not required. So we also have the readers and writers locks. So again, readers writer lock allows multiple threads to have simultaneous read-only access to an object protected by the lock. It also allows a single thread to access the object for writing at one time. Again, while excluding all readers. When the lock is acquired for writing, it takes on the status of write lock. Then all threads again attempting access for reading or writing must wait if one or more readers have acquired it. So we also have the condition variables, which is normally used to wait until a particular condition is true. So the condition variable must be used in conjunction with a Mutex lock. This implements a monitor of a type, illustrated again in figure somewhere in our textbook. Also, Windows provides synchronization among threads as part of object architecture. So most important method, as we can see, executive dispatcher objects, user mode, critical sections, and slim reader writer locks and condition variables. Then lock-free operations. Here, the dispatcher object make use of wait functions. And we first describe wait functions and then look at the synchronization method. So first we talk about the wait function. And again, the wait function allow a thread to block its own execution. Also, wait function do not return until the specified criteria have been met. And the last is the type of wait function determine the set of criteria that we'll be using. Now we go to the concept of critical sections. So critical sections, we mentioned this in our previous chapter, which normally provide synchronization mechanism, similar to that provided by Mutex objects, except that again, critical sections can be used only by the threads of a single process. So again, similar mechanism to Mutex, except the critical sections can be used only by the threads of a single process. Now, if the system is multiprocessor, then the code will attempt to acquire the spin lock. So as we said, again, critical sections provide a synchronization mechanism, which is again similar to the Mutex object. So event, mutex, and semaphore objects can also be used in a single process application, but critical sections provide a much faster, more efficient mechanism for mutual exclusion synchronization. So the process again is responsible for allocating the memory used by the critical section. Typically, again, this is done by simply declaring a variable of a type critical section. Then the condition variables are normally Windows. So Windows also has a condition variables. The process must declare and initialize the condition variable. Now the process must again declare a condition variable and initialize it in some thread by calling the initialize condition variable. So condition variables again can be used with either the critical section or the SRW logs. So we have again two methods. We have the sleep condition variable CS and sleep condition variable SRW. We sleep on the specified conditions. So Windows also relies heavily on the interlock operation for synchronization. Now, interlock operation use hardware facilities to guarantee that memory locations can be read, modified, and written in a single atomic operation. So examples include the interlock increment and also interlock compared exchange. We know many of the synchronization primitives use interlock operations within their implementation. But these operations are also available to programmers for situations where they want to synchronize without taking a software lock. Now, next is the Android. So Android interprocess communication. Here the Android again had to the kernel a new capability known as Bender. Normally, Bender provides a lightweight remote procedural call capability that is efficient in terms of both memory and also processing requirements. So the RPC mechanism works between two processes on the same system but run on different virtual machines. And that will be, again, the conclusion of our final section of chapter 6. Again, this chapter 6 covered the concept of deadlock and starvation, but we chose 3 operating systems and we discussed about the mechanisms that they use to avoid deadlock and also starvation and also the prevention of it. So again, wish everybody the best and thank you for your time.